Okay, welcome everybody. It's time to get started. Um, I hope everybody is healthy and safe. Today we have a special guest, Jenny Huang, who's a PhD student here in ECS. And I asked her to come and talk about her work because we're at the point in the semester where we're looking at design examples. We looked at the list processor the other day, and Jenny's been spending the last couple of years looking at how to build circuits for accelerating uh, deep neural networks on using primarily FPGAs. And so I thought it would be good to hear from her because this is a few design examples, how you see functions get mapped to hardware. And also, everybody's interested in neural nets these days, so it seems like it would be a good idea for you to learn something about neural nets. And then also, the way Jenny's been doing this work is using high-level synthesis, and I mentioned that the other day, and that's the idea of designing not so much with Verilog, but starting from a high-level language like C in this case. So you'll hear a little bit about that and see that in action as well. Okay, so I'm going to just turn it over to Jenny now. So take it away.
Should I share mine or?
I think you're sharing now.
Okay.
I see it.
Yep. Hi everyone. Hope you're all hanging there and stay safe. So I'm gonna start today's lecture on deep neural network accelerators and high-level synthesis. So here's the outline of the topic I'm gonna cover. So first, I'm gonna just briefly introduce you to the deep neural network workload and talked about the design methodology when we start designing an accelerator. And then we're gonna talk about different architectures for this deep neural network accelerator. And lastly, we're gonna talk about a bit of the tools that we use that's called high-level synthesis to help us to improve our productivity. So here I'm going to start by how people start to design the neural network architecture. So this diagram here shows a drawing of biological neuron in our brain. So the basic compute unit of the brain is this neuron, and there are like 86 billion of neurons in our brain. And they're connected with approximately 10 to the power of 14 to 10 to the power of 15 synapses. So, so each of these neurons will receive input signals from the dendrites, which is here, and then produces output signals through the axon, and then which interacts with the dendrites of another neuron, so that we can kind of pass the signal through all our nervous systems. So note that these SCM also produces what is called the synaptic weights, so that these weights are learnable, and can be controlled through the a signal density. Can kind of control the strength of each signals that pass to the next neuron. So this is how our brain processes signals we receive from the outside. And the design of neural network in machine learning is basically inspired by this biological structure. So from here, this slide. So this slide shows a biological neural network. So there are usually feed-forward computational graph constructed by the many computational neurons. So these computational neurons we show here, they typically first aggregates the signal they receive from the neighboring neurons. And then we perform an affine transformation on these input signals, which is represented as X here with different weights. So this is basically a dot product, and then we add up these signals together. So this will just integrate all this weight, all these input signals with different weights. And then based on this, we will choose whether to fire this signal to the next neuron. So the firing process is typically implemented by a nonlinear activation function. One example would be the function called ReLU. So the ReLU function will keep the signal that's larger than 0 as it is, and leave the rest to 0. So that if the signal is negative, then it will try to ignore the signal from the current neuron. So this is how we have a nonlinear functions in this neural network architecture. So next. So typically when we try to have a neural network, there are two processes to gather this structure working. The first process will be training. So it will be resemble how human trains. So first we'll have a training data set, like the different images that we're trying to learn from, and then we give each of these things labels. So as we grew up, our parents told us, okay, this is dog, and then we kind of established the connections between this image with this label in our brain. So it's likewise in neural network, the training process is similar. So we give the neural network the training data set and the label, and then we perform backpropagations or some other training algorithms to update the weights in the neural network. So it's like optimization process to minimize the error rates when we're trying to predict from this training data set to the label. This process is typically done in the cloud because it requires a lot of computation. And after we train this neural network and gather the weights of the networks, so we can directly perform inference. So we don't need to perform any backpropagation to change the weight. So now the weights is being fixed. So we can use this trained model to estimate the outcomes of the new inputs. So given the new inputs, we hope that the network can predict the right label. And this process is typically deployed at the edge because, as at the edge, we all normally just need to do the inference directly without reaching a lot of data set to retrain. Otherwise, it might because if we only train with certain data and labels, it will cause a bias in your model, which make your prediction not accurate. But nowadays, we're seeing more and more deployments of training at the edge because of security issues and concerns. Next. So with that, I'm gonna talk about the realm of the hardware domain right now. So there, as John introduced, deep neural network is a very popular topic right now, and there are a lot of chips being developed these days. Does anyone have a guess why that people need to develop like specialized chip for the deep neural network workload? So have John introduced you like the Moore's law and Dennard scaling in the lecture? Okay, so what Moore's law says is that the transistor density doubles every 2 years. So we know that is slowing down due to the physical limits of the material. And then, so what's Dennard scaling? So I think Dennard scaling is pretty much assuming the power density is a constant, meaning if the transistor size can get smaller, the power will get also smaller power number of each chip. However, this is not true as the transistor gets smaller and smaller. So actually the power density will increase because the power does not scale with size due to the leakage currents and the threshold voltage that's also probably been talked about in this class. So this created a power wall that limits the practical like processor frequency to around 4 gigahertz since like 2006. So since 2006, we see very few improvements in the processor's frequency. And therefore, so we cannot simply rely on the technology scaling to have a faster and more efficient processors to deal with these type of a general purpose processor to deal with this kind of new workload. So one solution is to develop like specialized accelerators, so we can eliminate this like unnecessary like control pipelines from the processors to deal with like general workloads, right? So that's why people start to develop specialized accelerators. But then we also need to customize these accelerators to different scenarios. So we can see these different chips that's being designed has very different specs due to its deployment scenario. So pretty much at the edge, in the edge, and the cloud. For example, in the cloud, it probably requires more flexibility or generality because people would like to train and inference and do more workload on the server because this chips typically is very large and kind of require a lot of like NRE to develop these type of board. And once it's in the cloud, you probably will hope it to be more versatile so that it can deal with more workload, more different type of models, and to be able to also train these models. So if you, on this left side of the slide, you can see that typically these chips on the cloud would have a throughput of tens of teraflops and have really large on-chip memory that can do pretty high precision computation because we need to really do training on the cloud. So when we do training, we require to have floating point processing units in this chip so that it can perform backpropagation. And also we want it to be very high performance, but then with this high frequency typically consumes more power. It's very power hungry. And at the edge, we see much more efficient chips. So on the edge, people typically focus more on like power efficiency because we're assuming the devices have like a battery, and then we probably would like to consume less energy for the device to last longer. So in this case, these will have way less compute capacity with less memory on them, on-chip memory on them, and then they sometimes will just only compute lower precision workload. So they don't have any capability of performing high precision computation. They only are composed of like low precision computation units in order to keep them very small and efficient, and they run at lower frequency so that this consume less power in this case. So typical design here would be like an Intel Movidius, which has like a very like 4 kiloflops computes on the edge, and then Semicon 1M is deployed on a Huawei's phone kind of thing. So these are kind of like typical AI like neural network accelerators at the edge, and then on the cloud there are like Google TPUs, and you can also think of like NVIDIA's GPUs as deep neural network accelerator here. And there are a lot of companies here because AI is very it's a hyping field, but it's very important. It's very exciting for people to see if people can automate workloads with AI. So here are like a whole spectrum of the chip that's been developed. So on the horizontal axis, we kind of just compared them. They're like a compute throughputs. So whether they're device focused or the cloud focused. If they're cloud focused, they're more on the right side with higher compute throughputs. And then the y-axis is the generality. So how flexible these chips are. So it really depends on the deployment scenario to have to trade off these like different spectrums here. Next. So I think here, this slide, we will want to just mainly talk about that computer vision tasks are mainly, so pretty much ConvNet become the mainstream state-of-the-art solutions for the computer vision tasks. So before, we have a lot of machine learning algorithms such as SVM and kernel methods to probably like manually craft some of the features, but then with ConvNet being very the most powerful solutions, I think most of these computer vision tasks are turned to deep neural network instead of using the traditional method to predict their labels. So this wide range of like computer vision tasks includes the image classification, object detection, semantic segmentation, super resolution, and activity recognition. They are needed on a variety of applications, such as autonomous vehicles, security cameras, drones, medical imaging, robotics, and mobile applications. So we see these being widely adopted in many different application domains already. So here I'm gonna just introduce the more detailed deep neural network architecture for you. So the algorithmically. So here are the typical common operations you're gonna see in most of the deep neural network designs. So they include convolution, red loop pooling, fully connected, and batch normalization. So I'm gonna talk about them one by one. So for convolution, the input to a convolution, we typically use input image as its inputs. So for input images, they typically have like 3 dimensions with RGB channels. And the intermediate data will have more channels in this neural network after we perform convolution. So we refer to these inputs and intermediate output as the feature map. And then we'll have our weight kernels, which is we mentioned in the previous slides. It will be like the synaptic weights for the brain or for the neuron to perform dot product with the inputs, so that we can have different impact of different inputs on the final decision that we make or the labels we recognize. So for the weights that of a full convolution, it typically has 4 dimensions. So the input channels, so it will be matching the input channel of the input image and the width and height. So that will be just the kernel, the weight kernels width and height. So it's typically like 3 by 3. So it's a lot smaller than the input images width and height. And for the output channels, it determines the number of channels of the immediate output images of the convolution. So here's an example of convolution. So for each input image, now we'll have IC input channels with width and height of, like, for example, 512 to 512. And then with each weights, well, this input channel of each weight will match the input channel of each image. And then for each one of them, we'll have a 3 by 3 kernel, for example, height and with height equals to 3 and width equal to 3. So we'll perform a convolution with weights and inputs. So each convolution will produce only one output feature map. And then we'll have 4 of these weight channels. So which will be, after we convolve this input image with these 4 different weights, that will produce us an output image with 4 different channels. So this is basically how convolution works. So if we look at it spatially, what it does, so what we mean by convolution with the input with the weights will be, we'll have a weight filter, which is this moving square of value 10123, 1012. And then, so on the left, it shows convolution with 3 by 3 convolution with no stripe, no padding. So meaning that we have a 3 by 3 receptive field, and then we just directly perform a dot product on the weights and the inputs. And then we put each of the output to each output feature map pixels here. Likewise, if we have a 3 by 3 convolution with stripe 2, that means that once we move the filter, we'll skip this input feature map by 1 because we have stripe 2. So every sampling field is interleaved by 2 offsets in this case. And then we perform the dot product with, on the weights and the inputs, and then store the output of the dot product to the output feature map. So this is the basic computation of the convolution on the spatial level. And then as on the channel level, as we mentioned, that we just kind of perform, for example, 4 of these, so output channel number of these convolutions spatially, and then we'll generate output images with different number of output channels. And the next one, so here's like a 3D animation of how convolution works. So this is how we produce one output channels. So if we have multiple of these kernels, we can produce output with more output channels. Um, and then the next typical layer that you're gonna see in neural network will be called fully connected layer. So essentially it's a matrix vector multiplication. In the FC layers, we assume the input will be flattened into a 1D array instead of a 2D image array. So each input activation will be connect to every output activation, which means that what it does is the input activation. So this is the input vectors. And then we'll have a weight of, which is a matrix of size OC and IC, like of input channel size and output channel size. And it will produce a new vector that's of the output channel size. So it performs a matrix vector multiplication on the input and the weights and then produce an output vector. It's pretty straightforward. It's just a matrix vector operation. And the next I'm talking about the ReLU, which is the activation function that introduces the nonlinearity in the neural network, which is a very important part of the algorithm because it is really the introduction of the nonlinearity kind of like pretty much increases the modeling capacity of neural network compared to the traditional models. So this is implements the concept of firing that we mentioned in our brain structure. So it pretty much is a rectify linear units. It pretty much says if this input value is larger than 0, I'll just keep it as, and if it's less than 0, that just keep it to 0, so that in this case, we can only fire the signals that's above a certain threshold, which means that it's important to us. Note that this function is only non-differentiable at 0. So note that all these operations in a neural network must be differentiable for it to be updated. So when we train these neural networks, people typically use backpropagation since it's one of the most efficient way to update the neural network's weights. So backpropagation requires all these operations to be differentiable. But then if it's non-differentiable at 0, it's still acceptable because all the other regions that we can approximate. And then next. The next layer that people use in deep neural networks is called the batch normalization layer. So this batch normalization layer shifts and scales the activations so that it can center the distribution of the input to 0. And then it can also normalize its variance with like a unit variance. So what the computation is also pretty simple. So with each batch of input, so normally when we train our inference network, we don't just use one image. We use more than one image. So typically that size will be like 32. So for each batch of the inputs, we kind of just calculate its mean and its standard deviation. And then when we actually do training and inference, we kind of just subtract each input in this batch with the mean of this whole batch and divide it by the mean of this, divided by the standard deviation of this batch. So here is like a mathematical equation for the batch normalizations. The next thing we gonna talk about is it's called the pooling layer. So with the deep neural network, we kind of just keep, kind of increase the capacity of the information we get from each image, right? So with that, we can kind of encode a lot of weights in the deep neural network architecture. But then once we need to predict the output, we only need a few outputs from each layer. So one way to downsample the image. So once we gather enough information, we need to downsample and filter out the non-important ones. So what we use is called pooling. So there are different pooling operations. One typical one is called the max pooling. So the max pooling takes the maximum value from the spatial dimension and then just outputs the largest one. For example, if our pooling filter is of size 2 by 2 in this example on your left, so that it will just look at these 4 different fields and take the largest one and outputs the largest one to the output feature map. So that in this case, we can downsample the informations, and then once we have like I'll talk about the overall architecture of the DNA later. But so this operates at each feature map level independently. So for each feature map inside each inputs, it will be done independently. And also for all different images in different batch, and in the same batch, it will be operated independently because it's a very input dependent operation. So here is the full DNN example, which is the AlexNet. So it's kind of like the first very like a known to be working like state of the art deep neural network in 2012 that kind of beats all the other algorithm designs for the image classification. So if you look at this AlexNet infrastructure, like this architecture, so it kind of takes the image of size 3, and then with height and width as 224 and 224. In between, you kind of increase the channel sizes of the feature map so that it can kind of gather more information for this network. And then at the end, it does like a mass pooling to downsample this input image dimension. And then once it downsamples to a smaller spatial dimension, you kind of just flatten it out to an FC, so to a vector. And then using this vector, you can kind of do the FC transformation so that it will produces the labels of size. For example, here's it should be 1,000 here. I don't know why is it 2. So the accuracy of AlexNet. So when we look at the DNN model, what we care about, one is accuracy. So for the top one accuracy here, that means that how accurate this model can predict if out of its top 1 prediction is correct. So here it means that when we look at this image, the network will give the probability of different labels. So whether this label of top 1 probability is correct. So that ratio is 57.1. And then the top 5 accuracy means that this model will also give like a probability of all the labels, right? Just pick the top 5. And if the correct label is among these top 5, that means this is correct. So the top 5 accuracy is normally higher than top 1 accuracy. And the model size is the weights that we need to store to calculate this output for this neural network. So the model size is pretty much all this size sum up from all these layers summed up. And the MAC means that how much compute you need in order to compute the labels for one image, for example, to go through one neural network architecture to produce this label. So in this case, it's multiply and add counts. So in this case, if we have, I don't know if I have an example here. Yeah, but pretty much it just kind of like adds up all the total compute like of convolutions in each of the layer. So it gets to this number. So a better model would be a model that produces higher accuracy with less model size and smaller max to us. And a newer network that will be a ResNet. So that it kind of introduce more structures in the neural network. So this is called a residual connection. So that we sometimes want to skip of the information of certain layers. So that to keep such like the information, for example, from the beginning to the end, we can kind of just skip this through this skip connections. So in this case, there's probably less overfit in this network. And then we can see that the network can achieve higher accuracy with smaller model size and smaller MAC. And there are a lot more neural network design nowadays that can have better performance with less model size and less MAC. So I encourage you to just look it up online, and then you'll find a lot of different models. And there's a website that listed all the state-of-the-art models for each task, such as image classification and object detection. So if you have interested in this, I encourage you to Google them up and look at the new structures, because nowadays they have very different structures, and sometimes they have new operations. So from the hardware designer perspective, we will need to look into those and think about our designs and see if we can accommodate our hardware design with their new network architecture. So next is the design methodology. So once we have this workload, what we need to design next is how do we design an accelerator for this workload? So from the previous slides, we kind of get a sense of what the basic compute unit would be for this accelerator. However, we don't know, like, okay, how do we really compose all this information and then decide on what units we want to have, how many units we want to have for each operations, right? So here is one model that we normally use for judging whether accelerator is good or not. But then this also kind of describes the workload, and we also like characterize the workload with the relationship with the workload and the architecture we're looking at. So first I will teach you how to really compare different architecture based on these roofline models. So the roofline model pretty much says that the peak performance of an accelerator is either bounded by the peak performance of the communication bandwidth, which is this tilted roofline, or the peak compute performance, which is the pi here. And which design points your workload will fall into this roofline model is really dependent on the operational density of your workload. So it's also called operational density. It's also called arithmetic intensity. So in this case, the roofline describes what our hardware looks like, because when we design our hardware, we kind of know how many PEs we'll have, which will have impose how high this total flops will have. Flops means gigaflop, floating point operations per second. So how many like PEs, compute unit we have will kind of decide this, will determine on this like pi roofline here. And then the bandwidth between these compute unit versus between and the DRAM will be determined by this like tilted roofline. So it will be it will just like this slope will be the peak bandwidth, I think. Yes, that will be the peak bandwidth of your memory to the PE. And then what determines on which points your design will fall is actually workload dependent. So the workload dependent arithmetic intensity is the ratio of compute to the memory traffic of your own workload. So it's not hardware related, it's more related to your own algorithm. So for example, if your algorithm, so once if I load one weight, if it can be used by, for example, 10 different inputs, so then I will say that operational intensity of that operation of the weights actually will be 10, right? So the point will be fall into this line. So the x-axis will be here for that workload that I described. So in this case, we can see, if the operational intensity, so I can perform 10 multiplications with one loads of this weights, then the operational intensity of this weights will be here. So in this case, it is compute bound. So which means it's, so we can kind of determine okay, we can roughly estimate the performance of that workload running on your system. And if with the lower arithmetic intensity workflows, for example, if we can use the weights once it's on chip only once for one multiplication, and then we need to kind of dump it, then the arithmetic intensity will be kind of like just be 1. In this case, it will be like memory bound. So in this case, there are two ways to improve this workload. Either you can improve the memory bandwidth to your PE so that the slope of the P and beta and I will be steeper, so that it wouldn't fall into the memory bound region. Or you can try to optimize your software workload to make it use the on-chip loaded weights more. So in that case, if you change your algorithm, you can also just move your points from 2 to 10. So in that case, you can move that horizontally to a more efficient region with higher arithmetic intensity. So here is a roofline model that we see from the GPU paper, I believe, for CPU, GPU, and TPU. So all these solid line here are the hardware roofline. And then all these points listed in this graph are the workloads. So LSTM is a model for an NLP, natural language processing. And MLP sometimes is used for like ranking models, like recommendation models, like deep learning recommendation models for like advertisements and stuff. So we can see they have very different arithmetic intensity, so that their x-axes are very different, right? So this x-axis kind of like of these workloads determined by its own characteristic, which is the operational intensity, which is the arithmetic intensity. And then we can see, so their y value should be like their throughput should be determined by the roofline. And if they're not strictly following the roofline, that means that there are probably more space to optimize in the software. But then you can see in all these like examples, it's kind of like roughly following the roofline, except for the stars, for this star, for example. So, but then other ones, for TPU, it's following this roofline pretty well. And also in this example, we can see a specialized accelerator can sometimes perform much better because you can put more specialized compute units, for example, for the multiply and add in this accelerator compared to the other hardware such as GPUs and CPUs. So on GPU, so here I'm going to talk about how this convolution is mapped onto the hardware. So one way people are trying to come up with a deep neural network accelerator is just to directly design a matrix multiplication engine. So that's very general purpose because it's also pretty much widely used in high performance computing. So matrix multiplication, like we also call it GEM. It's kind of like a very, very common workload nowadays already. And then one easy way to directly deploy this workload onto hardware or existing engine would be just directly map the convolutional 2D to matrix multiplication. And then it is done through an operation called M2Call, which stores in each column the necessary pixel for each kernel map. But then it requires the input feature map to be duplicated in memory. And then we also need to kind of restore the output feature map structure in memory because we kind of flatten them out when we're trying to map the convolution 2D into matrix multiplication. So in this example, we can see that for the, actually I will talk about how it's get mapped later. So here we kind of just roughly say that, like, see the dimension of how we flatten these M2Call, like the convolution 2D into matrix multiplication. So in this case, for the input layer, we directly flatten them into K square. So K is actually the size of the filter here, and then C is the number of input channel sizes, and N should be a multiple of H and W. Likewise, so for the weights, we map them into D. D is the number of like the output channels. K is the kernel sizes, and C is the number of input channels. So the output tensor will be of size D times N. So D will be the number of output channels, and N will be a multiple of height and width. And how this is done typically is that so for each of the filter, the weight kernel filter spatial dimension, we need to kind of flatten them out to the each column or each row of this input matrix. So each K here, the K in this image will be the height and width of the kernel, the multiple of the height and width of the kernel. So here's some more detailed illustration of how this is being mapped. So for example, for the first convolution, we need to compute. All it does is pretty much does a dot product of this 2x2 receptive field. And how it gets flattened is we kind of put 1, 2, 5, 6 into one column of these input matrix. And then for the second input value that we need to convolve the weights with will be, which will be, I have an animation here, 2, 3, 6, 7. So we also just flatten them out into this input matrix column. And likewise, so that's why we said we need to kind of duplicate the input value in this input call process in order to turn them into a matrix-matrix multiplication operation. So yeah, likewise, so we see like 3 has been reused here, and then like 6 has been reused here. So that's how we flatten this 3D input into a 2D tensor and can be still used to produce the convolution outputs. So with this being multiplied by the weights, so here is the flattened matrix of the weights, I believe. And produces reshaped output. So okay, I think it's the same image. So here is still the input, and then we also need to reshape our weights so that once we have how many weights. Oh. What? Kernel 12. Each kernel is of type. So I think that the 12 will be the number of total output kernels we have. So it's still like the input channel. So this, assuming we have only one output channel dimension, and then with 12 input channel dimension. In this case, we'll have 12 of these input channels, and then so that we kind of can match this 12 input channel dimension, and then we can directly multiply these two matrix together and produces an output of size 4 by 36. Yeah, I think that's how it works. But then after we transform it into the output, we still need to, again, we need to resize this output so that it will be turned into a 3D tensor again. The next way to realize this operation is to map the convolution 2D to matrix vector multiplication. So instead of performing into call, we kind of directly think of these operations as a matrix vector multiplication. So how it works is that for each pixel, so we're not considering the spatial dimension of the kernel yet. We first can perform for each channel. So assuming we have a 1x1 kernel for now, we directly multiply the input. So the input pixel size will be 1x1 because we're only taking one pixel of the inputs, and then we'll have an input channel size just IC here. And then we'll have a weight. We're not considering the spatial dimension of the weights yet. So if we don't do the spatial dimension of the weights, we'll have IC. So the input channel will match the input channel of the input image, and then number of different output weights will be the output channel sizes. So once we extract these values, we can compose matrix vector calculation to produce output of 1 pixels in this output image, the partial sum of 1 pixels of one image. So if it's a 3x3 filter, we kind of just need to do this 3x3 times, and then adds that value up to the partial sum of this current pixel. So this is typically how we turn the convolution 2D to matrix vector multiplication. So now we kind of know how we map this workflow onto the accelerator. Here I'm going to talk about some architecture and hardware to realize this operations that we mentioned before. So one architecture is just a systolic array. So what it performs is to just perform matrix to matrix multiplication. So it is a homogeneous network of tightly coupled data processing units. So the reason why they call systolic arrays, because I think the data just flows through the different PEs. So you have intermediate storage in each of these processing elements. So that means that each data processing unit here is independently computed partial results as the function of the data received from its upstream neighbors. And then it stores the result within itself. And it can also pass it down to other neighboring DPUs. So an advantage of these type of designs that you have shorter wires, because you don't directly connect the inputs from the memory to the processing elements. So it kind of introduces less like propagation delays, and it kind of introduces less like buses again and the routing, so that it lowers your total power consumption. It also enables higher degree of pipelining, because normally you will have registers on each of your PEs, and that enables a faster clock. It also enables high degree of parallelism, because you can have essentially a lot of them without affecting the total clock unit, like the frequency a lot. But also the control logic is very simple, because it's simply dependent on how the connection of these systolic array is, right? So there's no control to essentially determine which router, which DPUs each of the data is going to, because you kind of just feed it into the peripheral ports of the whole PE arrays, like the DPU arrays. And pretty much the execution of this workflow will be determined by the data flow on this hardware. So there's no extra control logic needed. So here is a very simple systolic array design. So typically we'll have, so here is just a MAC unit actually. Just we connect the multiply accumulation units in systolic array here. So what it does is pretty much computes the output of two matrix. So if you see from here, you typically put some on-chip memory buffers at the peripheral of these PE array. So this mesh of PEs will be called systolic array. And then we don't have any direct connections, for example, from memory to some like the furthest PEs that's not supposed to be connected. So it's only connected to the neighboring PEs, and then the neighboring PEs is passing its data to the next PEs. So in this case, we'll have input A coming from the left side, and then input B from the top. Then each of them will have a register to store them temporarily, and then we accumulate the output of the multiplication in the C registers in this systolic design, and we can accumulate this. So in this example, we can, for example, float the B with different K into the different C units. So essentially, once we adding up each of the partial sum here, we will gather the results of matrix C00, right? So likewise, we can do the same for other PE units. So by the end of this computation, after we feed in all these inputs from A and B, the register C in each of the P array will store the outputs for the output matrix. So next that we will have talked about more specialized architecture. So before the systolic arrays, that designs currently for the matrix multiplication. And as we mentioned before, that you can kind of use input call to map your workload into matrix multiplication. But we can also just keep the convolution as it is, so that we don't have to duplicate the data in the inputs. So what we have on FPGA normally it's a layer-based design. So in this case, we'll have buffers for, so this is actually a more comprehensive accelerator because we now have different layers included in this accelerator. So we'll assume that we'll have a pooling layer, ReLU, and batch norm. So this is kind of like typically how the data will flow in this deep neural network workload. So we first will have this is more like a system view. So we'll have a DDR, so we can store some larger data in your DRAM, and then, but then it takes longer to access the DRAM, so that we'll need to store them onto an on-chip buffer. So here are the on-chip buffers we have. It's typically of like size less than 32 MB, so it's less than the total model sizes. And we kind of can just stream the data through. For example, if we have a systolic to perform matrix vector multiplication, then I didn't list the detailed architecture here, but then we can fetch the input and the weights at the same time. And then we kind of stream that through different PEs. And then the partial sum is also, or the output is also produced at the meantime. So once the output is produced, that we kind of pass them through to the batch normalization layer, ReLU layer, pooling layer. If any of them is skipped, we can directly feed them out to the DRAM. And then here, so the execution model for a specialized accelerator is that for the hardware, we'll implement all these 4 different layers, like convolution, ReLU, batch norm, max pool, and FC layer. So this will be like the whole, note that the mapping of the FC will be similar to conv layer if you noticed before, because both of them, in this case, we're kind of mapping them to matrix vector multiplication, right? So in that case, the FC and conv layer and hardware are mapped onto the same hardware, but then we'll have specialized ReLU, batch norm, and max pool layer. How we map this AlexNet design is that we partition the AlexNet design graph. So first that we see, okay, that based on the number of like convolutions and FCs that you need to include in each subgraph. So in this case, the first layer will include all of them. So that will need to pass the input to the conv, and then to ReLU to batch norm, and then to pooling layer. Likewise for the second subgraph. So once this is executed, we will store the output back to the DRAM. And then for the next layer, we'll again load the data from the DRAM onto this accelerator, and then output it to the DRAM. And likewise, for the third subgraph that we see that we need to skip the ReLU and the batch norm. So in this case, we kind of just use the control signals to direct the output directly to be fed back to the DRAM instead. And likewise, we can map the whole graph onto this specialized deep learning accelerator design. And next week, I'm gonna talk about more spatial design. So a spatial design means that if you look at before, we kind of just mapped one layer of this subgraph onto the hardware. And now for the spatial ones, we're trying to map more layers onto the hardware. So what does that mean is that we will have, for example, convolution 3x3 and convolution hard by 1x1 unit hardened on our spatial hardware. So even for the FC, so assuming this is the hardware, but then we're customized our hardware units for each of the layers in the deep neural network design. So each of the sub part of the accelerator, we will need to have, for example, an on-chip VRAM to store the weights and the bias for each of the layer. Because as we put the data in and let them flow through this graph, we assume that the weights is on chip, otherwise the performance wouldn't be good. And then in this case, we don't have to skip if our subgraph, for example, does not have pooling layer. In hardware, we can just ignore that in this part of the network. And then likewise, we can customize the hardware for each layer on this spatial design. But then the trade-off is that we'll have smaller weight buffers and less PEs for each layer of the compute. But then we can achieve what's it called, the pipelining parallelism here, because once we start feeding the data in, we'll have data flow in each of the layers. So that means that we're trying to compute for different layers at the same time. So if you think about the processor design, it's like we will have instructions at each stage of this processor. So this is what we meant by spatial design. That means that instead of turning the computes into time dimension like this design, so for each of the step, we map the whole hardware to one step instead of, or we map more time dimension onto the spatial dimension, meaning that we perform more time step in the hardware at a time. So these are the two different designs that people can have for the deep learning accelerator on FPGAs. So we can also see there's a trade-off space between them. And it really depends on the workflow itself for us to determine which design will be the best. And the next I'm going to talk about is the line buffer design. So this is a fairly important design concept in FPGAs, or especially for the convolution, because the line buffer design pretty much says that once we have inputs, but then we want to reuse the input more. So before, what we talked about is that we store all the weights on chip so that we don't have to reload the weights. So we can achieve more reuse of the weights and improve the arithmetic intensity of this compute, because more weights are loaded onto the VRAM and they are keep reusing by the input that we feed into the accelerator. However, we can also improve the reuse of the inputs through adding a line buffer in this data flow. So now we have all the weights buffer on the VRAM, but then in 3x3 convolution, we'll have spatial reuse. So if you think about it, is that for each output pixels in your image, one input image pixel can be reused for the compute of 9 different output pixels. Right. So in order to reuse these input pixels, we kind of need to buffer them somewhere. So given that in convolution, the filter, 3x3 filter, we have. So assume we have 3x3 filter, and then we need to just slide them horizontally first. So in order to reuse the horizontal inputs, for example, if I have 3x3 here, I should be able to reuse the second to third column of this 3x3 filter in my next compute for the next output pixels, right? So that requires to buffer the first 2 lines of this input pixel dimension. And then as we slide, we can always reuse the buffered inputs so that we are not missing any opportunity to improve the arithmetic intensity in this workload. And then as we slide down, then we will, so first we will buffer all those 3 lines, and then as we compute, we can always reuse the data in this line buffer. And as we have new outputs, we will also, as we go down, we will just add 1 more line here, so we can also reuse things vertically that can be reused for the next output pixel. And then here, I'm going to talk about the execution model of the data flow. So for the pooling, what it does is pretty much just to take the maximum of this inputs. So what we have is like, we also need to have a line buffer here because we don't want to load everything from the DRAM and compare them onto the register. And then we also have certain reuse for different pixels. For example, this is, so here is actually one good example of line buffer, but then this is only for pooling, but instead of the input computation. So for the pooling, with a filter size of 2x2, here we can store the values of 1, 4, 2, 3. Actually, we don't have to store 1, 4, but then once we store 2, 3, it can be reused by the next pooling operations in this line. So 2, 3 will be reused by the next operations. And then we take the largest out of the 2, 3, 2, 5, 3, 8. Sorry, this is a little bit messy. Oh, and this one, in this case, we're actually assuming this pooling layer has a stride of 2. But then sometimes if it's stride by 1, then this line buffer design will help us to reuse the input that we already loaded on chip. That's kind of like the whole idea. And next, I'm going to talk about the high-level synthesis. So, so once we have all these ideas on how do we design this cellular architecture, it normally takes us a long time to write things in Verilog because in order to even achieve a line buffer design, we need a lot of debugging need to be involved, right? Like so for all these designs, we design it manually. It might take us weeks to have like a functional working systolic array with memory. So what high-level synthesis does is that it's another abstraction for developing hardware. So the reason why developing hardware is very hard and time-consuming, one is that like people need to specify register transfer level operations for each of the signals. And a lot of complicated controls has not been abstracted away. So once you specify one signal wrong in your Verilog, you need to kind of look into the waveform, and then it's very hard to find if one signal is wrong with like the RTL level abstraction. And especially for like the interface connection, which is very standard, should be done in a template way. It does not provide a good abstraction for you, right? And a lot of times for people, they're spending on, like, for example, debugging why loading of this data from the memory to this PE is off by 1 cycle. So that's not a very efficient way to design hardware. So what high-level synthesis does is they allow user to specify the algorithm logic in a higher level language like C, so that it kind of get rid of the concept of like a RTL level signals and clock. So we don't have to really worry about the time dimension of the programming. So it's kind of like really simplify the process to kind of specify an accelerator. And then this high-level synthesis accelerator can help us to, one is to map very high-level abstract onto low-level logic if it's just combinational logic. And secondly, kind of help us to easily specify the interface connections, which I'll mention later. And lastly, it kind of allow people to explore more architecture design questions rather than specifying cycle to cycle operations. And it automatically help people to pipeline the your design so that you don't have to do a lot of like retiming yourself, like moving the register around and messed up with your design. I can kind of like can help you automatically kind of optimize for the clock that you're trying to aim for by automatically inserting certain pipeline registers in your algorithm. So it seems it's a very powerful tools, but then current status of it's not like very ideal, because it's once it's automatic, it cannot optimize like cycle to cycle of performance. But then for FPGA, it's perfect because it greatly improves the productivity while not trading off too much performance. But for ASIC design, people are still like thinking about it, which I hope that this limitation can be pretty much removed or like improved by the current research in high-level synthesis to improve the real circuit performance. So the high-level synthesis compiler, what it does is generates the RTL based on the high-level descriptions. So from C directly to Verilog. So what it involves is that you need to first allocate resources for the required compute you specified in your algorithm, right? So once you have this resources allocated on hardware, you can schedule them based on the constraints you specified with the tool. The scheduling means that like what operation to run on each of the allocated resources at what time. And binding also pretty much binds certain operations to the allocated resources. So the decisions made by binding may imply sharing functional units between operations and sharing registers and memories between variables in a high-level language like C. And then, so here are different supported high-level languages for high-level synthesis current right now. So C, C++, and a lot of OpenCL, these are like imperative languages, and Golang, which let us to specify a more parallel abstractions. So Golang is a more a language for concurrent programming. So that allowed us to specify the explicit like parallelism in hardware. So like typical hardware mapping for high-level synthesis that normally in this, take a C for example, it will map a C function into a Verilog module and the function arguments either to memory ports or just to direct hardware signals. So, and then the basic block. So basic block is a block without branches in your C code, and that would just can be mapped into strict like direct hardware logic. And then the operations will be mapped onto function units, such as multiply will be probably mapped onto a DSP on FPGAs, for example. And then the arrays, the memory storage will be mapped onto memories like VRAMs. So here we're talking about all these structures as in FPGAs instead of an ASIC. And then the control flow graph, we typically turn it into a finite state machine. So this is how typically a typical hardware mapping from hardware synthesis looks like. So there are certain limitations on hardware synthesis abstractions that it does not support dynamic memory allocation or recursion, because in this case, we don't make no assumption of the hardware. So it's not like a CPU that has a stack or has a heap. So once we use C to specify for hardware, we don't assume any of those architecture exist in the hardware. So here's one design examples for matrix multiplication engine. So I'm gonna just talk about how to write a matrix multiplication accelerator in high-level synthesis, and you can see how easy is it compared to writing in Verilog. So first we need to specify the peripheral on-chip buffer. So in C, we can just simply specify them as local array. But then we also need to consider how many ports we would like them to have in this local array by specifying the array partitioning. And this is Vivado HLS, so that we, in addition to the array specification in C, we also need to have additional information for hardware saying that we would like to load these data in parallel. So that means that we need to have more ports or more banks for these local memories. And then how you specify that in high-level synthesis is just add pragmas to it. And then in this case, we'll have the local buffer for input A, local buffer for input bit, and local buffer for the output C. And all these dimensions need to be completely partitioned, meaning that we should be able to load the data from this memory at each cycle. Note that also the array can be mapped onto registers, so to any to any storage elements. But then there's also a pragmat for you to specify that. And then we can also have, so the next step in high-level synthesis is that with this very high-level abstraction, we're able to very implicitly kind of tell them that we want to perform a matrix multiplication. So here is a very implicit way to specify a systolic array. So you kind of just have very regular 3-level of loops. That's what you would write in software. And then pretty much like A val times B val plus C, and equals the result, and store the result back to the C buffer. So in this case, we can see that we put the pipeline here equals to 1. So that means that assuming we're turning all these inner 2 loops into hardware, we hope that we can feed the new data into this hardware every other cycle. That means that we need to have a buffer for each of the PEs to buffer the inputs and the output for this whole inner loop hardware. So otherwise, we're not able to achieve II equals to 1, or we might have more. But yeah, so that's how what does the II mean? Means the initial interval, means that how big is the bubbles between 2 pipelines. But then if you're not sure if you write it in this way, it will be turning into a systolic array. You can also write it in a very structural way. You can write your design explicitly in high-level synthesis. So this way, it will be very similar to how you write a systolic array in Verilog. You kind of just need to specify what data is being fed into the next elements and next registers, right? So in this case, you kind of explicitly says that, okay, for each of those local memories, like the registers, what it does is to get its value from the neighboring buffers, and then based on this neighboring buffers, what you will need to do for the next PEs, right? So, and then you probably want to you need to specify the compute for each of the output elements as well. So this is a very explicit way to write a systolically in HelloSynthesis. So you can write it either way, but then it really depends on how smart this HelloSynthesis compiler on how they can optimize your design. So next. So the innermost part is not so difficult normally because it's normally a very structured compute, and then it's mostly can be synthesized into combinational logic with pipeline. But then the harder part would be how do you specify things in control logic in high-level synthesis. So here, we first read the input image from the global memory. So here, the global memory will be specified as an also array. So a very good things about this is that we can put this A as a port, as an input to this accelerator functions. And then later we can synthesize this port. So we can add a pragma saying this port will be implemented in AXI so that this will generate the AXI protocol for you. And once you would do this loading data from A loc to the local A, the HelloSynthesis tool, like the compiler, will compile this down to specific AXI requests that need to happen in a certain time. So in that case, that simplifies the interface generation a lot, because a lot of times a lot of bug comes from how you specify the signals for the interfaces. So that's one very, very significant advantage of HelloSynthesis. So in this case, for the outer loop, we will have 3 decoupled reads from the A location. So note that all these 3 functions does not have to be executed in series because that there's no data dependency on them. So in this case, we can, even in C program, we can extract the instruction level parallelism from them. So in hardware, when it gets synthesized, this will be done in parallel instead of in series. So in this case, that we're kind of just loading things onto the local VRAM. Once we load the things onto the local VRAM, we can just start the execution of the whole accelerator. So there are many different resources that you can look up for how to design your accelerator HelloSynthesis. I think once you get one design working, the later iteration will become easier and easier. And then there are a lot of optimization you can also do with HelloSynthesis compiler. So I encourage you to look at the Vivado HLS design hubs, and then you can just play with HelloSynthesis with your pink board with IPython notebook. So it should be fairly simple, and then you can see how you can just write a C-like program, and then you can have hardware to accelerate those C-like programs. But then in order to optimize for these designs, you really need to look into the Vivado design example to see how they act the pragmas, because the POC abstraction wouldn't be enough for you to specify a high performance accelerator. And other than that, I feel like you also can look at some a structural HelloSynthesis design, which you can specify your design in System C, which is a language that allow you to specify also parallelism in your design through channels. So it's also explicit parallelism multi-threading models in C, so that a lot of sometimes a lot of ASIC design are designed using System C, because you kind of specify the design structurally in very fine-grained, explicit way, as we mentioned before in System C, and then all the signals are actually can be expressed as explicit what's it called, the concurrent processes in System C. So in that case, you can have finer grain control of how things are mapped onto hardware, so that you can perform more detailed optimizations there. So I think that concludes all my lecture slides. Yes. So if
Wow, perfect timing. It's exactly 5 o'clock. If anybody wants to ask a question, we could take a couple more minutes. Okay, well, I guess it was crystal clear then. Okay, thanks, Jenny. And
hope it's not too confusing.
okay, well, thank you very much. And everybody else, will see you. Have a good weekend. I'll see you on Tuesday.
You too.
Okay.
Have a good rest of your day.
Thank you.
Thank you.
Okay. Bye-bye.
Thank you. Bye.
Thanks, Jenny.
Thanks.
Okay, bye-bye.